Welcome back, my rubber hearts. Today we are diving into an important property of rubber that plays a crucial role in sealing, gasketing, and long-term durability: compression set. Whether you're working with O-rings, seals, gaskets, or vibration dampers, understanding compression set is key to choosing the right compound for the job. So let's break it down. What is compression set? How is it measured, and what do those results actually mean in real-world applications? To start, compression set is a measurement of how well a rubber material returns to its original shape after being compressed for a long period of time. When you press down on rubber, whether it's in a static seal or under continuous mechanical pressure, the expectation is that once the pressure is removed, the rubber should be springing back. But not all rubbers behave the same way. Some return almost completely to their original thickness, while others remain permanently deformed. Compression set quantifies this effect as a percentage. The higher the percentage, the worse the material is at recovering its shape. For example, if a rubber gasket has a compression set of 10%, it means that after being compressed and then released, it retains 10% of the deformation instead of fully bouncing back. A material with an 80% compression set, on the other hand, has almost completely lost its elasticity and won't seal properly anymore. So how do we actually measure this in a lab? The test follows a straightforward but precise procedure to determine how much permanent deformation the rubber retains after being compressed for a specific period under controlled conditions. A technician starts by preparing the rubber sample, which is typically a cylindrical disc of standardized thickness, often around 12.5 millimeters or 0.5 inches, depending on the test standard. The initial thickness of the sample is carefully measured using a thickness gauge to establish the starting point. Next, the rubber sample is placed between two rigid metal plates and compressed to a set percentage of its original thickness, usually 25 or 50% compression, depending on the standard being used. A special fixture, either a clamping device or spacers to maintain uniform compression, is used to hold the rubber in place to ensure that the deformation remains constant throughout the test. The sample is then placed in an oven at a specified temperature, which is typically 70 degrees or 100 degrees, or even higher for extreme aging conditions, and held there for a predetermined duration, often 22 to 70 hours. Once the heating period is complete, the sample is removed from the fixture, allowed to cool at room temperature for 30 minutes, and then its final thickness is measured. The compression set percentage is then calculated. This process is carefully controlled because even minor variations in temperature, compression force, or cooling time can affect the results. The test tells us how well the rubber recovers after prolonged deformation, which is critical in real-world applications like seals, gaskets, and vibration dampers, where maintaining shape and elasticity over time is crucial. Now, let's look at the different standards that define compression set testing. Several international standards dictate testing conditions for different industries, and, depending on the standard, the exact test conditions and measurement criteria might vary. The most commonly referenced standards include ASTM D395, ISO 815, and DIN 53517. While they all measure the same fundamental property, the specifics of the test, like temperature, duration, and test fixtures, can differ. ASTM D395 is one of the most widely used standards, particularly in North America, and it defines two test methods, Method A and Method B. Method A is called the compression set under constant force test, where the rubber is compressed with a specific force rather than a set distance. Method B, on the other hand, is called compression set under constant deflection, where the sample is compressed to a fixed percentage of its original thickness, typically 25% compression, and then exposed to a given temperature for a specified duration, usually 70 hours at 70 degrees or higher for heat aging tests. After the test period, the sample is released and allowed to recover before measuring how much thickness has been lost. The ISO 815 standard, commonly used in Europe and globally, is similar but sometimes differ in temperature selection and compression levels, depending on the material's intended application. DIN 53517, which is widely used in Germany and parts of Europe, follows a similar approach but may have different fixture requirements. The differences between these standards are often based on historical testing preferences in different industries or specific material behavior considerations. Some standards might be stricter in terms of test setup and conditions, especially for critical applications like aerospace or high-performance automotive seals. Another point to consider is that different devices are sometimes used for compression set measurement. In some cases, metal spacers are used to control the exact amount of compression applied to the sample. In other cases, special compression set jigs allow for higher precision when testing very thin or sensitive materials. The choice of testing device depends largely on how accurate the measurement needs to be and the type of rubber being tested. Now, let's talk about what compression set values actually mean in real life. Different polymers exhibit different compression set behaviors, and this has a direct impact on how they are used in industry. Let's start with EPDM, a material known for its excellent weathering and ozone resistance. In its sulfur-cured form, EPDM has a much lower compression set, making it ideal for high-performance O-rings and static seals in the automotive and industrial sectors. Silicone rubber, on the other hand, can have exceptionally low compression set values, especially at extreme temperatures, which is why it is the preferred material for food-grade gaskets, aerospace seals, and medical applications. However, some formulations of low durometer silicones can exhibit high compression set, which is why careful selection is needed when using it for high-pressure seals. NBR is widely used in oil and fuel applications, and depending on the cure system and formulation, it can either perform well or suffer from poor compression set. High acrylonitrile NBR compounds often have better fuel resistance, but sometimes trade off elasticity, which means they might not recover as well after long-term compression. Fluoroelastomers tend to have very low compression set values at high temperatures, making them the gold standard for seals in aerospace, chemical processing, and high-performance automotive applications. Their ability to maintain shape and elasticity in aggressive environments means they are often chosen for critical sealing applications where failure is not an option. In contrast, NR and SBR generally have poor compression set resistance, making them less suitable for long-term sealing applications. But they are still widely used in vibration isolation mounts and dynamic applications where high elasticity is more important than maintaining a perfect seal. The testing and measurement of compression set might seem like a simple concept, but it has a massive impact on how rubber products perform in the field. Choosing the wrong material can mean premature failure, leaks, and costly downtime, while selecting the right polymer and cross-linking system can extend service life and improve reliability. Thanks for turning into my rubber heart. If you enjoyed this episode, don't forget to like, subscribe, and hit the bell icon so you never miss an update. Let me know in the comments, what's been your experience with compression set issues in rubber applications? Have you ever had a seal or gasket fail due to permanent deformation? I'd love to hear your thoughts. Until then, see you next time.